Relational versus document databases today. There are many differences to consider when comparing relational databases to document databases, including their fault tolerance properties. See Chapter 5 and handling of concurrency. See Chapter 7. In this chapter, we will concentrate only on the differences in the data model. The main arguments in favor of the document data model are schema flexibility, better performance due to locality, and that for some applications it is closer to the data structures used by the application. The relational model counters by providing better support for joins and many-to-one and many-to-many relationships, which data model leads to simpler application code. If the data in your application has a document-like structure, i.e. a tree of one-to-many relationships, where typically the entire tree is loaded at once, then it's probably a good idea to use a document model. The relational technique of shredding, splitting a document-like structure into multiple tables like positions, education, and contact info in Figure 2-1 can lead to cumbersome schemas and unnecessarily complicated application code. The document model has limitations. For example, you cannot refer directly to a nested item within a document, but instead you need to say something like the second item in the list of positions for user 251, much like an access path in the hierarchical model. However, as long as documents are not too deeply nested, that is not usually a problem. The poor support for joins in document databases may or may not be a problem, depending on the application. For example, many-to-many relationships may never be needed in an analytics application that uses a document database to record which events occurred at which time. However, if your application does use many-to-many relationships, the document model becomes less appealing. It's possible to reduce the need for joins by denormalizing, but then the application code needs to do additional work to keep the denormalized data consistent. Joins can be emulated in application code by making multiple requests to the database, but that also moves complexity into the application and is usually slower than a join performed by specialized code inside the database. In such cases, using a document model can lead to significantly more complex application code and worse performance. It's not possible to say in general which data model leads to simpler application code. It depends on the kinds of relationships that exist between data items. For highly interconnected data, the document model is awkward, the relational model is acceptable, and graph models, see graph-like data models on page 49, are the most natural. Most document databases and the JSON support in relational databases do not enforce any schema on the data in documents. XML support in relational databases usually comes with optional schema validation. No schema means that arbitrary keys and values can be added to a document, and when reading, clients have no guarantees as to what fields the documents may contain. Document databases are sometimes called schemaless, but that's misleading, as the code that reads the data usually assumes some kind of structure, i.e. there's an implicit schema, but it is not enforced by the database. A more accurate term is schema on read. The structure of the data is implicit and only interpreted when the data is read, in contrast with schema on write, the traditional approach of relational databases, where the schema is explicit and the database ensures all written data conforms to it. Schema on read is similar to dynamic runtime type checking in programming languages, whereas schema on write is similar to static compile time type checking. Just as the advocates of static and dynamic type checking have big debates about their relative merits, enforcement of schemas in database is a contentious topic, and in general there's no right or wrong answer. The difference between the approaches is particularly noticeable in situations where an application wants to change the format of its data. For example, say you are currently storing each user's full name in one field, and you instead want to store the first name and last name separately. In a document database, you would just start writing new documents with the new fields and have code in the application that handles the case when old documents are read. For example, on the other hand, in a statically typed database schema, you would typically perform a migration along the lines of: schema changes have a bad reputation of being slow and requiring downtime. This reputation is not entirely deserved. Most relational database systems execute the alter table statement in a few milliseconds. MySQL is a notable exception. It copies the entire table on alter table, which can mean minutes or even hours of downtime when altering a large table, although various tools exist to work around this limitation. Running the update statement on a large table is likely to be slow on any database, since every row needs to be rewritten. If that is not acceptable, the application can leave first name set to its default of null and fill it in at read time, like it would with a document database. The schema-on-read approach is advantageous if the items in the collection don't all have the same structure for some reason, i.e. the data is heterogeneous, for example, because there are many different types of objects, and it is not practical to put each type of object in its own table. The structure of the data is determined by external systems over which you have no control, and which may change at any time. In situations like these, a schema may hurt more than it helps, and schemaless documents can be a much more natural data model. But in cases where all records are expected to have the same structure, schemas are a useful mechanism for documenting and enforcing that structure. We will discuss schemas and schema evolution in more detail in Chapter 4. A document is usually stored as a single continuous string, encoded as JSON, XML, or a binary variant thereof such as MongoDB's BSON. If your application often needs to access the entire document, for example, to render it on a web page, there is a performance advantage to the storage locality. If data is split across multiple tables, like in Figure 2-1, multiple index lookups are required to retrieve it all, which may require more disk seeks and take more time. The locality advantage only applies if you need large parts of the document at the same time. The database typically needs to load the entire document, even if you access only a small portion of it, which can be wasteful on large documents. On updates to a document, the entire document usually needs to be rewritten. Only modifications that don't change the encoded size of a document can easily be performed in place. For these reasons, it is generally recommended that you keep documents fairly small and avoid writes that increase the size of a document. These performance limitations significantly reduce the set of situations in which document databases are useful. It's worth pointing out that the idea of grouping related data together for locality is not limited to the document model. For example, Google's Spanner database offers the same locality properties in a relational data model by allowing the schema to declare that a table's rows should be interleaved nested within a parent table. Oracle allows the same, using a feature called multi-table index cluster tables. The column family concept in the biddable data model used in Cassandra and HBase has a similar purpose of managing locality. We will also see more on locality in Chapter 3. Convergence of document and relational databases. Most relational database systems other than MySQL have supported XML since the mid-2000s. This includes functions to make local modifications to XML documents and the ability to index and query inside XML documents, which allows applications to use data models very similar to what they would do when using a document database. Todd's original description of the relational model actually allowed something quite similar to JSON documents within a relational schema. He called it non-simple domains. The idea was that a value in a row doesn't have to just be a primitive data type like a number or a string, but could also be a nested relation table, so you can have an arbitrarily nested tree structure as a value, much like the JSON or XML support that was added to SQL over 30 years later. PostgreSQL since version 9.3, MySQL since version 5.7, and IBM DB2 since version 10.5 also have a similar level of support for JSON documents. Given the popularity of JSON for web APIs, it is likely that other relational databases will follow in their footsteps and add JSON support. On the document database side, we think DB supports relational-like joins in its query language, and some MongoDB drivers automatically resolve database references, effectively performing a client-side join, although this is likely to be slower than a join performed in the database since it requires additional network round trips and is less optimized. It seems that relational and document databases are becoming more similar over time, and that is a good thing. The data models complement each other. If a database is able to handle document-like data and also perform relational queries on it, applications can use the combination of features that best fits their needs. A hybrid of the relational and document models is a good route for databases to take in the future. Query languages for data. When the relational model was introduced, it included a new way of querying data. SQL is a declarative query language, whereas IMS and Codicil query the database using imperative code. What does that mean? Many commonly used programming languages are imperative. For example, if you have a list of animal species, you might write something like this to return only the sharks in the list. In the relational algebra, you would instead write, where sigma, the Greek letter sigma, is the selection operator, returning only those animals that match the condition family equals sharks. When SQL was defined, it followed the structure of the relational algebra fairly closely. An imperative language tells the computer to perform certain operations in a certain order. You can imagine stepping through the code line by line, evaluating conditions, updating variables, and deciding whether to go around the loop one more time. In a declarative query language, like SQL or relational algebra, you just specify the pattern of the data you want, what conditions the results must meet, and how you want the data to be transformed, for example sorted, grouped, and aggregated, but not how to achieve that goal. It is up to the database system's query optimizer to decide which indexes and which join methods to use, and in which order to execute various parts of the query. A declarative query language is attractive because it is typically more concise and easier to work with than an imperative API, but more importantly, it also hides implementation details of the database engine, which makes it possible for the database system to introduce performance improvements without requiring any changes to queries. For example, in the imperative code shown at the beginning of this section, the list of animals appears in a particular order. If the database wants to reclaim unused disk space behind the scenes, it might need to move records around, changing the order in which the animals appear. Can the database do that safely, without breaking queries? The SQL example doesn't guarantee any particular ordering, and so it doesn't mind if the order changes. But if the query is written as imperative code, the database can never be sure whether the code is relying on the ordering or not. The fact that SQL is more limited in functionality gives the database much more room for automatic optimizations. Finally, declarative languages often lend themselves to parallel execution. Today, CPUs are getting faster by adding more cores, not by running at significantly higher clock speeds than before. Imperative code is very hard to parallelize across multiple cores and multiple machines, because it specifies instructions that must be performed in a particular order. Declarative languages have a better chance of getting faster in parallel execution because they specify only the pattern of the results, not the algorithm that is used to determine the results. The database is free to use a parallel implementation of the query language, if appropriate.